Yeah, so now we start recording. So today I'm gonna talk about, introduction, both in terms of the logistics and also in terms of like some basic things about the course and what we should expect. Okay. So a little bit of introduction, administrivia, any question that you might have, and then we're gonna, if we have time, we're gonna talk about some of the basic concepts here. Okay. So about me, I kind of recently started at UCLA. So this is the third time that I'm teaching this course. I graduated in 2020 at Georgia Tech. I did my PhD in computer science, and my bachelor was in electrical engineering. My master was also in electrical engineering. My research mainly is about computer architecture, but with the flavor of security. Throughout the course, I'll also talk a little bit about security and why it's important. And I'll also do lots of things in embedded system security. In terms of doing research, I'm gonna come back to the slides later on at the end of the course. But if you're interested in these topics, I'm always looking for enthusiastic and talented students like you. So do feel free to reach out to me and talk about the possible research possibilities in my lab. Also will teach another undergraduate course next quarter about security. I'll talk about that also later in the quarter. So if you're interested, please consider that too. I have two cats, which you're gonna see a lot in this course, and this is also my wife. I'm from Iran, so this is actually so we celebrate what's called Nowruz, which is like the beginning of the spring, and this is like a special occasion that we have. So this guy here is PJ, and this one is Meadow. So as I said, it could be very important. You'll be asked about them. The big question is how to pronounce my name. My first name is Nader, with like the A is actually like long, and my last name is Sehatbakhsh. It's very, very difficult to pronounce it. I know. So to make your life a little bit easier, you can call it with the first part, the Sehat part, or just call me Professor or Professor Sehat. I'm also totally fine if you call me by my first name, Nader. Okay, but please don't call me Dr. Nader or Professor Nader. That's a little bit weird. So contact information. The easiest way to contact me about the course is direct message me on CampusWire. Okay, I'm the most responsive there. If you send me an email, I usually go through lots of other emails that I have. But if there's something like urgent or private and you want to, like it's a longer message, then feel free to email me. Office hours would be mainly by appointment, but I also have the 5 to 6 p.m. on Tuesdays open. My office is actually in the same building on Boulter Hall, 6th floor, 6371G. So you have to go into this a hallway, which lots of different rooms are there too. And then mine is G as in George. If you cannot open the first door if it's locked, then just message me or email me and I'll come in. But usually try the door, it's usually unlocked, okay? Or just most of the time it's actually propped open. We have two TAs in this course, very good TAs. Justin is a second year PhD, he's actually working with me. And he was TA for this course last year too, so he's pretty experienced. Shayandeep is a master's student, second year master's student who also worked with me, and he's also very experienced. He hasn't been TA for this course specifically, but he actually taken this course with me, so he's very familiar with all the details. He's also very experienced in computer architecture. He has done lots of internships in big companies like Google and AMD, specifically on computer architecture. So if you have ever, talked to him, ask him about his experience, and he can give you some feedback about what would be like to be like a computer architect in these big companies. Okay, their emails are listed here and also on the website. Same as me, the best way to contact them is through CampusWire. So just direct message them. One quick note is that there won't be any discussion session this week, okay? So nothing tomorrow. So the first discussion session would be obviously next Wednesday, okay? Also, feel free to ask questions along the way. So if you have any question, just raise your hand. Our first few sessions, please also introduce your name so that I can kind of try to remember it. I'm not gonna promise, but I'll try. So the lecture format would be in person. As you can see, I'll try to record everything. So in the past, I had a success of recording everything with good quality, and usually it's posted online after a few hours after the lecture. You can find it either on YouTube or directly on the website. Attendance is not required, but it's strongly encouraged, except for the quizzes that I'm going to talk about, which are going to be in person, so you have to actually come here. But what usually happens is that around like 50% of the class prefer to watch the lectures at home or whatever with their own pace. They usually maybe speed it up or speed it down, watch it multiple times, and I have no problem with it. But I also want you guys to be here to ask questions, so we have this interaction, because your question will be helpful for you and also for everybody else. But if you watch the lectures, unfortunately, you won't have that opportunity. So it's on you whether you want to decide to come to the class or not. Okay. But if I see nobody's coming to the class, which usually doesn't happen, then I have to enforce some sort of rules that's at some point you have to come to the class. So about the COVID, masking, not masking, and all those things, we're gonna follow whatever guidelines that UCLA is providing to us. And what I'm gonna do is probably going out and in, I'll probably just wear my mask, and given that there is some distance, I'll probably won't wear my mask when I'm doing my lecture. You guys, it's your decision whether you want to put your mask on or not. But obviously, just try to follow the science and follow the guidelines. Okay. So about the logistics, so all the slides in PDF going to be uploaded prior to each lecture on the website. This is the link to the website here. Change the color. So everything about this course, including the videos and materials and everything, will be available online here. And you don't need to even be enrolled in this class to access these. So feel free to share it with anybody else who is interested. Previous year materials also can be found. You just need to change this F22 to F21, and you will see the same exact website and all the lectures and everything. I'm assuming that everybody has access to all the homeworks and quizzes, past homeworks and past quizzes as well. So that's also totally fair if you want to use them. Okay. The notes that I'm gonna put right on this iPad won't be shared with you. I used to share it in previous years, but I feel like it's better not to share it so that you actually kind of write your own notes, because I got the comments that people think that it's going to be useful and it's not. So I think it's better to actually not share these notes with you. Okay, but obviously you can watch the lectures, and the lectures are available. So if there's something important I've written, you can always go back and find it. Discussion sessions won't be recorded. I know that many of you would like these be recorded, but we won't do that for multiple reasons. First of all, discussion sessions are meant to be like the interaction between the TAs and the students. So you have your lectures, you can watch it as much as you want, but the discussion session is something that I want you guys to go if you're interested, and ask questions and interact with the TA. Okay, so it won't be recorded because of that reason. The second reason is just pure logistics. It would be tough for the TAs to record everything with good quality and so on. So I don't want them to go through this hassle of recording things. Okay, and also the notes that TA is going to make also won't be shared unless you go and nicely ask them. Then they probably just email it to you guys. But again, the whole point is for you to take notes and do whatever you think is important for that specific session. Okay. So these are kind of the rationales. Again, we want you to give you as much as information to help you to learn things. And these decisions are kind of made based on my past experience in the previous offering of this course and other course that I've been to. I might change if you, like all of you really, really want to have the notes, then at some point I might give in and give you the notes. But for now, that's the plan, okay? All right, so we're going to use, as probably most of you already know, we're going to use this website CampusWire. How many of you have used CampusWire before? Show of hands. Okay, so almost everybody. I think most of you have already enrolled. The last time I checked, it was like around 100. So I think it's still like, 50-ish people are still haven't been enrolled. In order to enroll, you have to go to Brunel, and I'll actually listed how you can enroll on CampusWire. So please do that as soon as possible, because we're not going to use Canvas/Brunel in this course. So it's on you to actually go and enroll there. So CampusWire would be our primary place to post announcement, and also to have all the Q&A about the lectures. Any problems that you have, you're strongly encouraged to actually post the questions. In the past offering of the course, we have very, very lively discussions on CampusWire, and it's like one of the main things that people really enjoyed about this course. So I hope that you guys also contribute, and your contribution is also both from asking question and answering each other's questions. So the plan that we have with TAs is that we're gonna check it regularly, but we're not gonna answer all the questions quickly. We're gonna give you some time to actually you read the questions and you answer the questions, each other's questions, because the process of answering also would be very helpful for you to learn more about the topics. Don't be afraid if your answer is incorrect. Even if it's completely incorrect, we're gonna read it and we're gonna suggest the correct answer. So whatever comes to your mind, just put it there, and that's totally fine. Okay. And then also don't feel bad about asking simple questions, stupid question, whatever you want to call it. There is nothing like that in this course. Okay, so whatever question that you have, the most basic question you think it's there, just ask it there. One thing we want to minimize is duplicated questions. So when you're asking questions, you also make sure that you're up to date with all the posts on CampusWire, because something that might happen is, especially when we reach to the project part, people are going to ask the exact same question that the previous person also asked. So use the information and the knowledge that already exists there. Okay. But generally, any sort of participation is highly encouraged. You can also post about things that are interesting to this topic as well. So if you've seen some other articles or something like that you think it's also relevant, that could be also posted on CampusWire. Okay. You can also create groups in CampusWire. You can also create private groups in CampusWire, which I won't see. So also feel free to utilize that option. I know in the past people used things like GroupMe or Discord to also discuss things offline. That's also totally fine and highly encouraged if you want to use that. I'm sure it's already there in these different platforms. So participation actually not only encouraged, but also we're going to grade, give you some grades for that. There will be also some bonus points for participation. So again, I strongly recommend you to participate in the course. Any questions so far? Yeah. I'll get to that part when we are talking about the grading. So the question was, what was the class participation score? And how do we score? How do you grade your class participation? There is a textbook. For some reason, I forgot to put it in this slides, but it's on the website. So it's the Hennessy and Patterson book. It's a very, very famous book by these two very famous people, actually. Patterson is a professor at UC Berkeley, which is now retired. Now is part of Google and also his own company. Hennessy used to be the president of Stanford. I'm not sure if he's still there or not. But yeah, they have this book called Computer Organization. And I think the full name is something else. But yeah, the computer, so they have two famous books. The one that we're going to use is the computer organization one. And make sure to buy or rent or get the RISC-V edition. The second edition and then the RISC-V edition, okay? Because they have the ARM edition, they have MIPS edition. Make sure to get the RISC-V edition. One thing to note is that the book is not required. We're going to assign you some readings, but the readings would be optional. So it's not like you have to really buy it. You can also find it online if you want to. But it's very helpful. Many of the things that we discuss in this course also would be extensively described there, but we're not going to follow exactly what the format that they're going to follow. Okay. Any other questions? But the full textbook is actually, if you go to the website, if you go to the home directory, you will see the name of the book and everything. For what? For exams? For quizzes? Yeah. Once we get to the quizzes, I'm going to describe the logistics of the quiz. But yeah, it's open note, open book, open laptop, whatever you want. It's just not open chats or open discussion. But anything else, feel free to bring it. You can actually bring your own laptop if you want to. Any other questions? The homeworks. We're gonna use probably our own our own questions. If there's something from the book as well, we probably just put it on the PDF itself, so you don't have to search for it. Okay. All right. So in terms of exams, so no actual midterm or final. We're gonna have 3 quizzes. Last time we offered the course, we had 4, but I felt like 3 would be better because we can space it a little bit more and have the quizzes. The quiz would be in person, as I said, and it's going to be probably around 1 hour. You will have your either piece of paper or laptop, whichever you prefer. So the dates would be these 3. It would be on Tuesday of week 5, Tuesday of week 8, and the last session of the class, which is the Thursday of week 10. The quizzes are kind of like, the first quiz is kind of like, takes a lot of time to get to the first, then a little bit time to the second, and then very short time to the third. This is specifically done because, things are getting denser once we get, closer to the end. So that's why we probably just do one topic for the third quiz versus more topic for the first quiz. And another thing that you will notice is that the first half of the class would be more of like more heavy on the project side. So we're actually whatever we're gonna discuss in the course, you're gonna actually implement it as I'm gonna describe in the next few slides. So the first half of the course, you'll kind of like, deal with more project, and the second half more with the quiz. So this is kind of like intentional in this sense. If you cannot attend these days, so you have to reach out to me as soon as possible so we can find another way to figure out what you can do. In the past, we did like Zoom-based attendance as well, but that's not something that you can choose. If only as emergency circumstances come up, you can go with the Zoom mode as well. Okay. But I'm going to talk more about the quizzes once we get closer to it. We're going to have a few homeworks. So homeworks would be usually very short. So like one homework probably just takes like 1 hour or so, hopefully. I'm thinking about like having between 5 to 6. I think last time we had 5, but depends on the things. Later half of the course, we might also have, mini like coding questions in the homework as well. Once we get to that point, I'm gonna describe it to you. We're gonna use Gradescope for downloading and uploading and grading your questions. I'm gonna automatically enroll all of you to Gradescope. If by next week you're not enrolled on the Gradescope, just message me on CampusWire. Okay. Usually we're gonna release it on Fridays, but there might be also other days that we might release it. There won't be a late submission, unfortunately. So if you miss it, you missed it. And usually we have 1 week for submitting the homeworks. But then again, homeworks would be like very in line with what we discussed in that week. So it's kind of as you're like looking at the lecture, you should be able to hopefully answer the questions as well. So projects, we're gonna have 2 kind of larger projects, and as I said, might have some mini questions as well in the homework. Your projects would be on C or C++. If you absolutely hate C or C++, then you can use Python as well or other languages. But we're gonna give you a skeleton in C, okay? So if you want to use Python, you have to start everything from scratch. The whole point of the project would be, the whole point of the project would be basically what we're gonna discuss in the first half of the class of how to design a processor. The cool thing is that you're gonna actually write that processor in C, and then your project would be basically having a simulator that actually can read instructions and execute instructions and creates you the results. The first one would be a single cycle. We're gonna describe what single cycle is, and then the second one probably would be a continuation of the first, and it's gonna be about branch prediction and forwarding and things like that, the more advanced part of the processor. The submission again would be through Gradescope. We might have some late submissions under some circumstances. Yeah. No, we're not going to use Verilog. We're going to use C and C++, but it's as if that we're using Verilog. We're gonna create what's called a simulator, which is basically acts like the actual processor. So we're gonna describe what is the actual processor in hardware would look like, different components, and those components becomes the functions in your code. So you actually have to like kind of emulate or simulate the behavior of those. Virtual machine is actually a technical term that it has its own meaning. We're actually going to get also to virtual addresses and virtual memory and virtual machine later in the course. By virtual, you mean, yeah, it's a virtual CPU, but because the term virtual actually has a meaning in computer architecture, I don't want to use that specific term. But yeah, if you think, yeah, it's not a real processor, it's a simulator of that processor. Other questions? Cool. For honor students, we're gonna do a little bit different for the projects. Those of you who are in the honor section, we're gonna discuss it in the honor class specifically. And one thing to note is that tomorrow we're not gonna have an honor discussion session as well. Okay, so our first class will be next week on Friday. If you're not on the honor, just don't bother. It's not relevant to you. All right, so this is the most important part of the class. The grading. So the grading would be project, homework, quizzes, and participation. Project's going to be 30%, homework 20%, quizzes 45%, and participation 5%. Back to your question of how do we grade participation? 2 ways. Either your participation on CampusWire. So if you actually go to CampusWire, you will notice that there is like a score assigned to you, like a reputation score. That would be primarily what we're going to use. And the way we're going to use it is usually in the past you use it like you have to have at least like 40, and getting 40 means that you have to post like 2 questions or answer a few questions, something like that. So hopefully throughout the quarter you have the opportunity to do that. One thing that I noticed that happens is that toward the end you start seeing this random question posted on CampusWire. Because on week 10, you notice that, oh, my score is 20. So let's actually ask this question of like, how's the weather like tomorrow in LA? Or you can do those things as well. But again, as I said, the whole point is for you to encourage you to participate. I'm not going to be stingy on giving you the grades. And most of you will get that grade anyway. But yeah, just try to participate it naturally, So be like, ask valid question and answer valid questions. No, it's just going to be based on completion. So homeworks would be just completion, unless the mini assignments, which would be basically the final value that you're going to put. But the quizzes would be both, based on the accuracy. Okay, so homework we want you to give it a try and write your answers. Okay. Any other questions about grading? You're welcome to discuss the questions, but of course, by no sharing means no sharing of your answers or your codes, right? So no cheating, in other words. Any other questions? We also will have some bonuses. Part of the project might be bonus, usually for class participation, mid-quarter survey, and end of the quarter survey. We usually also have bonuses. And we typically, if we see that, there is, let me actually go to the next one. Yeah. So if we see that, all quizzes are particularly so difficult, or this quiz is very difficult, we're going to scale up that quiz as well. But last year and the previous year, I would say more than 80% of the class got an A or even more. So number of A's are ridiculous. I'm actually trying to see if there are ways that I can get less A. But I personally prefer to give you as much as work possible. So my strategy is you just pushing it as much as possible so you actually learn something. But at the end of the day, also get good grades. So having both of both boards, getting good grades and also learn something. This would be the grade breakdown. So if you get above 90, which as I said, most of you will, you get an A. Above 85, you get A minus, 75, and you can see the rest, okay? One thing we will do is that we're gonna drop one of your homeworks, no question asked. So out of 5 or 6 or whatever number of homeworks that we will send it to you, you can just skip one. If you're busy, if there's something emergency happen, and that can be considered as you're dropped. In the past, when we had 4 quizzes, we also dropped 1, but I decided let's do 3 and count all the 3. So if you go back to the previous year, you will notice that we had that option, but we no longer have that option, unfortunately. And then the project, obviously, there is no mercy. You have to actually, submit both of them. Okay. Because that's a very, very critical part of the class, because you're going to learn things that we're going to discuss in the class with projects. Any other questions? Yeah. The format of the quiz would be similar to your homework. So few questions that you need to either fill in or calculate something and put some number and things like that. Yeah. We will post the answers to the homework. The TAs will. So the plan is usually the TA will discuss it during the discussion session, and then we're going to also formally post it on CampusWire. Previous years' answers are not there, and you cannot find it unless you actually find a friends who are previous year's students, or you find some way to enroll on CampusWire as a previous year. The reason for it is that we want you to first try it. And if you want, you can ask the TA and they will provide the solution manual to you, okay, for the previous years. But feel free to use that as your practice examples as well for both the quiz and for your own homeworks. The discussion section, has a conflict. Yeah, you can. I'll actually talk about that. Yeah. Any other questions? Cool. All right, so to just kind of recap of the things. So the course website, as I said, is this link here. Everything regarding the general information, my contact information, TA's contact information, the syllabus will be there. The most important part is if you go to that schedule, tab, that's where you see this giant table of all the PDF and videos. Your homeworks will be posted there. Your project will be posted there and everything. Okay. So that's where you will see all these things. And as I said, if you change this to F21, you will see last year information too. So CampusWire would be used for announcement, Q&A, discussions, and direct messaging me. And Gradescope would be submitting all the assignments, including the project and your quiz and your homeworks and everything else. Okay. So that's kind of the 3 things that we're going to use, and we're not going to use Canvas anymore. All right. All right, so some general question that I I got lots of emails in the past few weeks about this. So as I said, no honors discussion session or regular discussion session tomorrow. So we're gonna start those from week 1. You can attend other discussion sessions if you want. You don't need to just go to the discussion sessions that you enroll in. The only problem would be if large number of people just go to one discussion session and there won't be room for people to sit. In that case, the TA has to figure out a way to kind of like accommodate everybody. If the problem persists, then we have to ask those people who are not enrolled in that session to find another session and go to that session, okay? But hopefully that won't happen. So just FYI that if we ask you to not go to that discussion session, that's the reason, okay? If you're on the wait list, I think only 2-3. Sometime this week I actually assign PTs to everyone. So you probably can just enroll right now. But if you recently decided to enroll, come and talk to me. We are kind of reaching to the end of the size of this class, and that's the cap. I personally, I can take as much as students as they want to, but the problem is the physical location. Given that we're going to have an in-person quiz, we cannot have bigger than 173 or something, which is the number of seats in this room, okay? And I think we are very close to that number. So people who wants to enroll, they have to come and talk to me, and then we should figure out the number of seats. You cannot attend this lecture online via Zoom, although I'm going to use Zoom to record it. You cannot join this Zoom. The reason for it is that there's going to be lots of problems with the voice and the feedback and all those things because this is a big classroom. So if you cannot attend, or if you're sick and you really want to attend for that specific session, you have to just watch the videos. And the Campus Wire is there for you to ask your questions. So hopefully we can accommodate you that way. And then if you just feel like to watch the lectures in your own time, just do it anyway, okay? But yeah, the hybrid format is not available. Unless of course, we go back to, the dark days of doing everything on Zoom. And then in that case, everybody has to join Zoom. TA office hours, not office hours. We'll be also announcing Campus Wire. We're going to do it by demand based off the project. So in general, the discussion session, part of the discussion session, usually the last 15 minutes would be used for answering individual questions. But other than that, there won't be any specific TA office hours. You can ask and schedule appointments with them, same as me, okay? All right, any other questions that we didn't cover? Yeah. On the website, on the main website, on the sysarc.ee.ucla. This one. Yeah, here. What's that? Usually once I go back to my office, if I don't have like an immediate meeting or something, I typically try to remember to post it. If I didn't, then there's somebody in Campus Wall which just posts something that, oh, you forgot. And by the end of the day, I will say most of the time I'll post it. Yeah. First assignment probably would be next week, end of next week. And then your first project would be the week after, most likely. So we're going to post it end of next week, probably on Friday. And then the deadline would be the week after. And the same for project mostly. The exact dates, I'm not going to promise anything because it might depend on like whether we have time to finish a lecture, and sometimes it moves to the next one. In the past, I always say, oh, we're gonna post it on Sunday. And sometimes we didn't, and people get like, confused. So yeah, that's why I'm not gonna say exactly Fridays, but most likely will be Fridays. No. Yeah. It's not recommended. I mean, it's kind of oblivious because I think M116L is actually going through Verilog as far as I know. And I decided at the beginning to do that, but I noticed that there are people who actually don't have any Verilog background. So yeah, it's slightly different. Yes, if you want, I mean, very different strategies. You can like, focus on one specific topic in one quarter and switch to the other topics the next quarter, or you can spread it around to actually like make sure that you remember things. It really depends on you. There is no right answer, unfortunately. Yep. So the question was whether it's required to do M116L with this course or not, and whether you recommend to do those at the same time. And I'll try to repeat the questions because on recording it will not be captured. So, but sometimes I forget, unfortunately. Anyway, any other questions? Yes, the quizzes will be open note, open laptop, open everything. So feel free to bring as much as documentation and information as possible. But it's gonna be 1 hour, so we have to be quick. So the whole point is, for those tiny things that you need to memorize, you can go and quickly look at your notes. But for the other things, you kind of know exactly what you should do, and then you just have to do it. And then, of course, bringing laptops means that you can, secretly chat and all those things. We'll try to minimize it and catch it as much as we can. But of course, our system was also not optimized. So it's kind of like an honor system. So depending on you, whether you want to like learn something or you want to find, just the answer. And unfortunately, in ideal world, you would say, yeah, of course, I want to learn something. But in real world, sometimes you also have to. But if we catch something, we're going to have all the maximum disciplinary action possible. Okay, so just make sure to don't share and don't cheat. Okay, in none of these categories that we have. Projects, we're going to check your code and we're going to see the comparison and all those things. For your homeworks, same, and of course for the quizzes. All right. Okay. What time is it? Maybe have like a 2-3 short, a quick break, and then in the second half, I'm going to talk a little bit about some actual technical aspects of the course. Okay. So it's 44. We're going to start at 48. All right. Okay, so now we know that's kind of like what are the expectations and things like that. Let's actually now start the actual lecture. Of course, the first thing is that why are we taking this course and what the plan is to like what we are expecting to learn. And so computer architecture is going to be so at least the way that we're going to focus on is the interaction with the software and hardware. And I strongly believe that this is what every single computer scientist or computer engineer needs to know. And that's why it's really important to have some basic level of understanding, although you might not be working with that interaction with hardware ever. You might be like a pure, software developer or data scientist or system developer or whatever you're going to be. But you have to have a good understanding of how the hardware works, not just because it's nice to know, but because it directly impacts the way that you write your code and your design. And of course, if you decide to go a little bit lower in terms of abstraction to work with the operating system or the compiler or the database and all those things, you absolutely need to know how the hardware works and what are the limitations, what are the trends, where we are going, where we have been, and all those things. So that's why I think it's very nice and very important to have that understanding. And this could be like maybe your only exposure to these kind of topics in your curriculum. And what we have seen in the past is at the end of the quarter, when people talking about, the evaluation, I noticed that, initially they have below average, like below 5, if I remember the numbers, interest in hardware and in this course. And at the end of the course, they actually significantly shifted to the right. And we're going to talk about those things and hopefully get more interested of why these are important topics and why you should learn more about this. Okay. So things that we're gonna learn is we're gonna follow this like step-by-step story, and we're gonna start from the high level of software and say, okay, we write our own software and now we're kind of good at it. But what happens next is kind of like the story that we want to tell in this course, and it starts with this interface, this edge between what's like translate from hardware to software, and that's the instruction set architecture, or ISA. So that would be the first thing that we're going to discuss in this course. Once we have our ISA, the question then becomes that, okay, we have a list of instructions, but really the question is, how do we really run them on a piece of hardware? And that's the story of the components that we're going to put next to each other in order to actually be able to run those instructions. And that's what usually we refer to as the microarchitecture. So that's the next thing that we're going to focus on the course. Then we're going to talk about, okay, we have the microarchitecture, but that's like the thing that we designed in 1980 or something. Afterwards, as we're going to discuss, there are lots and lots of optimizations in order to make this processor faster and faster. And if you follow like this keynotes from Apple to Google and so on, you see that they're saying, oh, our processors go 50% faster than the previous generation and so on. And the question is like, how did they do it, right? So we're going to learn about the techniques that they use in order to make their systems faster. So we're going to talk about pipelining, speculations, parallelism, and things like that. So this is M116 course, if you're wondering. You're good? Okay. Then we're going to kind of like switch gear and talk about memory hierarchy as like an important part of the system that goes hand in hand with the processor, which the ones that are actually doing the logic and doing the analysis. Because at some point in our system, we need to also store things and remember things. And we're going to talk about caches and memory, main memory, and then we're going to talk about why we need a hierarchy in our systems. And finally, we're going to talk about multi-core systems, and we're going to see how we design all these things and scale it up to make it even more bigger and more parallel. We're going to talk about things like coherency and consistency and so on. This is kind of like would be the first half of the class, and this part would be the second half of the class. Your projects would be mainly about these 3 bullet points, and the rest of the class would be about all these other things that we're going to discuss. And if we have time, usually at the last week of the class, we're going to talk about some advanced topics as well, maybe a little bit security, GPUs, and things like that, which is not going to be part of your like quizzes, but it would be nice for those of you who are interested to learn more about those things. All right, so this is kind of like our roadmap in this course. And as I said, we're going to start from all the way from the software and go all the way down to the hardware. And hopefully by the end of this course, we will see something like this and we are able to say all these words on what is like, GPU, what is a fabric, what is a GPU, why we have this, architecture and so on. So we're actually going to revisit this particular picture at the end of the course and you will see that you understand it fully. As most of you might already know most of things about this anyway. All right, so let's actually now talk a little bit more about the details. So the first thing is, okay, how do computers work? And when I'm talking about computers, I'm talking about the full stack. All right, so the way it works is that if I want to give you like a very simplified and dumb answer, is that we see computers as this box that we write some programs in some language. We just give it to it, and magically something happens, and something is printed or given out, and that's how we know that the computer works, right? At the end of the day, all these apps are piece of programs that runs on this box, and this box magically runs them and give us the interaction that we want. This interaction could be in sort of like a digital interaction with us, or it could be even actuation. It could be like moving a motor or making a sound or whatever it is, right? To give you a little bit more detail, we basically think that this box is not just a big black box, but it's actually a box with layers, okay? So it's not just, this is software and this is hardware. In reality, what happens there are multiple layers that this program goes through, in order to be actually executed and generate the results for us. And we define these layers as what's called an abstraction layer, which again, you might know already about this. And this abstraction layer is actually what is really, really interesting and what allow us to develop this very, very complex system, which is we call computer, without actually needing to know every single detail about the system. So if you are a software developer, you really don't need to know exactly how transistor works. If you are a transistor engineer, you don't need to know the details about classes and objects and all those things, right? All these people can work together in this very orchestrated and nice format just because of this abstraction layer, just because of this kind of like contract that we have between these different complexities. And what happens is that whichever layer that we decide to work on, we're going to think the rest as a black box, right? So if I'm an operating system engineer or designer, I'm going to say that, oh, there's going to be a compiler, there's going to be a software developer or a programming language that's going to give me this. Then I'm going to design everything, all the details about the operating system in my design. And then I'm going to pass it to another black box, which is the hardware, and the hardware going to magically run this for us. Now that we are at the computer architecture level, we actually now need to go down and think about, okay, how the hardware actually implements and execute this. But we're not going to go really, really down at the transistor level because it's, again, it's outside of our expertise. So we're going to stay at this layer, which is usually the macro architectural level, which is going to say that, okay, we are given set of instructions. How should we execute them? And our basic blocks are these RTL blocks that we're going to talk about: flip-flops, ALUs, main memory, and things like that. Again, we're not going to care how these smaller blocks like flip-flop, how they're designed and so on. That's a separate course that some of you may take or may not take. But here we're going to stay at that macro architectural level. Okay? Again, if you have any questions, feel free to just interrupt me and ask questions. And if you can, please just say your name so I can also kind of know you a little bit better. All right. So again, as I said, the main benefit of this is that in order to be working on software, you don't need to be an expert in computer architecture. But as I said at the beginning, you need to have some basic understanding, because the way you're going to write your program is going to directly impact that layer, and the change that we make at the computer architecture level going to also goes up and impact your software. Okay, so these goes hand in hand, especially now that systems are getting more complex. You even need more of this information. All right. So a simplified abstraction, if you want to, like, very simply, put how computer works, is that we need kind of 3 levels of abstraction. We need the application software, we need the system software, and we need the hardware. Okay. So let's actually go through these in more detail. So application software is what's basically what we do from an algorithm and put it in actual piece of code. We can use what's called a high-level language like C, Java, Python, and so on and so forth to do that. So basically, application software is this transition of what we just in plain English we want to do versus what we actually write down in some language. Then the system software is going to take this program and use a process compilation or compiler to translate this high-level language or HAL to what's called a machine code or assembly code. And then the operating system, which you can consider as this piece of software, is going to take this and kind of orchestrate everything there. So it's going to say, oh, we want to run this 4 different applications. One of them wants to read something from the sensor. The other one wants to interact with the keyboard. The other one is done and wants to print something on the display and all those things. So operating system itself is kind of like a program that's kind of handle all this scheduling and this file system management and all those things. And it's also very, very interesting topic, which you're going to take a course. Usually I see people actually taking the course with this course together in the same quarter, which is usually a nice thing to do, but again, not recommended. But operating system will service things like, handling inputs and outputs, managing the memory and all those things. And then the operating system going to hand off all these activities to the hardware, and that's where our story and our role kind of begins in this course, which is mainly three things that we're going to discuss and we're going to care about: the processor, which is kind of like the main component of the system. The processor will going to constantly interact with the memory, which kind of stores the information. And then we also have the IOs, the inputs and outputs, which we send and receive information, either going through the operating system and coming back, or directly to the inputs and outputs. Okay. Any questions so far? Cool. If you want to know more about abstractions, this is just all like a small YouTube video. It's just not that much, academic. It's more of like, just something to watch if you want to, if you're into YouTube. There's also interesting theoretical aspects of how a computer works and what is a computer. And if you have heard about Turing machines and what is a Turing machine, I also recommend to watch this multiple videos that I'm showing here. But we're not going to go through that part as well. What we're going to talk about is the realistic assumptions about the system and what the hardware actually does. All right. So to give you an example of the things that I just said, so we're going to start with some, high-level language, for example, a piece of C code. What happens next is, we're going to write, change the algorithm to the piece of code. Then we're going to use the compiler to translate this this part of C code to what's called an assembly language. In order to create the assembly language, we need to know which microarchitecture we're going to use. You probably heard about x86, which is like, Intel and AMD, and generally your laptops and your server use. That's one instruction set architecture. You probably heard about ARM. That's another popular one. You probably heard about MIPS and RISC-V, which is the one we're going to actually talk about in this course. These are all other different kind of like contracts that we use in order to translate this high-level language into this list of instruction, which is done by the compiler. And the story doesn't finish here, because the hardware does not understand ADD, number 2, and these things. The only thing that the hardware would understand is just series of zeros and ones. Okay, so it's going to say, oh, this is 0 or this is 1. Do I have to do this or do I have to do that? That's the only thing that the hardware would understand. So what will happen is that this assembly code is also be translated into what is called a machine code or binary code. And that's another process that we're also going to learn, that what is this contract between getting an assembly code and creating it into a machine code. And that's the job of what's called an assembler. All right. So that's basically the hardware representation of this problem, basically encoding the instructions into some numbers. And that's what the hardware would understand. OK. So basically, the life cycle, as I said, we start with some algorithm. The algorithm turns into some program, let's say a C program. The C program going to be compiled into an assembly code, which we're going to use RISC-V. And then this will be translated into just a series of seemingly complex or weird, like, sequence of zeros and ones. And this zeros and ones is what hardware would understand and would be happy about. So you can understand this, and we're going to show how this is going to be actually executed in hardware. All right. So this is kind of like, also kind of like a graphic of what I described. So we have a bunch of apps. And for now, we are at the abstraction level of the software. So we know nothing about anything below. So we're going to be just, oh, I'm going to write this software given this algorithm. Then there is hardware, which we think that this is this black box. The system software is the one that's kind of interact between these two. And then what will happen is that the hardware itself becomes the memory, CPU, and the I/O. And the problem would be that the first problem that we're going to see, and then kind of like figure out why we need an instruction set architecture, why we need this contract, is that we're going to use different languages like C, C++, Java, etc., etc. And then we can also have very different implementation of the hardware. The one that you're going to buy from Apple is very different than the one that you're going to buy from Google versus the one that you buy from Samsung versus the one you buy from Intel. So it's not like, you know, the exact same thing all of them are producing. There's completely different designs. So what we're going to face is that the system software is in this weird situation that it sees all these different languages and it's also all these different hardware, and somehow they have to magically make it work, right? Because like if you take your code and run it in your friend's laptop, it also works. If you run it on your cell phone, it usually works as well. So the question is like, how does this portability happens, right? And the answer to that is this thing called the instruction set architecture. So the story is like this: the hardware and the software come together and make this contract between them that say that if you're a software developer, do whatever you want you do with your code. At the end of the day, your code should be compiled or translated into this set of instructions that I know. We're going to talk about what is an instruction, but you know, add this register to that register is, for example, an instruction. So basically what happens is that the system software is going to tell the software that do whatever you want to do at your abstraction level, but when it comes to sending it to me, I'm going to only accept this list of instructions. So just you have to support that. And the hardware is going to also say that I'm going to do whatever I want to do inside my box, but I'm going to promise you that I'll be able to run all these instructions that we agreed on, okay? So, and that's the way that we're gonna do this compatibility between different hardware languages, different hardware implementation and different software languages, and even different operating systems. All of them knows the language of the instruction set architecture or ISA. And once they know that, then everything else can be solved automatically because you can do your own thing, but just translate it to this. And that's good, okay? So basically, the instruction set architecture, from now on, we're going to say the ISA is this interface between the hardware and software, this contract between them, which both of them agrees that whatever they do, it eventually leads to this. The software will translate it into the ISA, and the hardware will promise that they're going to be able to run all those instructions, okay? There are multiple different, and before actually going to that point, the big thing is that this means that the hardware and software are completely disjoint, and they can grow and they can be optimized independently, which is the big thing for the whole, you know, reason that we are actually at this point, which we have very performant hardware and very performant software, because hardware can make any changes internally as long as they can like still support all those instructions. Everybody is happy, okay? So kind of like in summary, what the software sees, and it's very important for us to understand this, is the functional description of the hardware. So what is the functional description? It's just two main things. The software should understand the storage locations, and we're going to talk about those as storage locations is usually either registers or memory lines or memory addresses. And the second thing is the operation. So for example, software will understand add versus multiply versus shift versus XOR and all those things, okay? So from hardware point of view, when they're trying to create a set of assembly languages, all they need to know is like, what operation do we need? And what are the sorts of like, you know, variables that we need to use? So that's what the software sees. The hardware sees the list of instructions, and there is a specific rule of how we create those instructions we're going to talk about in the next lecture. And most importantly, they order. So because the way, if you think about the way that we write the program, the order also does matter, right? So we're not like thinking that, oh, this function might happen before this function. When we are writing it this from top to down, we're assuming that this instruction happens before the other instructions, right? So the hardware sees that and understands that as well. And the assumption is that the hardware is also reliable and faithful to that order. Otherwise, things gonna be messy and gonna be incorrect. Okay, so this is kind of like, you know, the important things that you need to know about the ISA. That what software understand. When usually we say this is the architectural understanding of the software, which basically just only see how many memory addresses that we have, how many registers that we have, which register is part of like the memory as we're going to talk about, and then what are the operation that this hardware supports. Does it support multiplication or does it only support addition, for example? And on the other hand, hardware doesn't care about the software. It only care about this list of instructions that it knows, and gonna also know the order of those. So this is the things that we're gonna focus on for the rest of this class. There are a bunch of different options for your instruction set architecture. What we're gonna focus on is what's called a RISC-V. We're gonna talk about what is RISC and why there's this number 5 there. RISC-V is this open source instruction set architecture coming out of UC Berkeley about 10 years ago or even more. And these days it's getting much more popular, and especially in academia. Like you see most of the different courses are actually using that. There is no significant difference in terms of if you know RISC-V or if you had focused on ARM, what would have happened. All of them kind of follow similar rule of thumbs, but the details, of course, are a little bit different. But we're going to specifically focus on RISC-V because we had to pick something in terms of the details. So RISC-V would be the one that we're going to focus on in this course. And of course, the details would be all the lectures of next week. Okay? Any questions so far? Okay, so now we know that how computer works, and now we know that this important thing is the ISA, and that would be the first thing we're going to go and dive into. But before that, we need to also answer this question of what are the objectives, right? So if I want to create the ISA, what is my decision process? What is my thought process? What should I optimize and what should I don't care about, right? And that's like, what is the main objective of an architecting a computer? And maybe you guys can answer this question. Like, what do you think is the most important things when we are designing hardware? Anybody? Reliability, okay. Space, can you elaborate more? Okay. Speed, okay. What's that? Power consumption, yeah? Say it again. Cost, okay, yeah. These are great answers. And they're all right answers, but there's one that is more right than the other, and that's the speed. We need computers to be efficient in some sense. And the first thing when it comes to being efficient is your computer has to be fast, okay? Of course, it has to be also reliable, it has to be cost efficient, it has to be power efficient. But the number one focus in the last 30 years of designing computers is how fast your computer is, okay? And we usually call it performance. So the technical term which we use is the performance. So we want our computers to be performant and computers to be fast. And if you actually pay attention to all these sales pitch, usually the first thing that they're going to say is that our computers, our new design is 10x or this number and such number faster than the previous version and so on, right? But of course, there's other things that we need to care about. And as I'm going to tell you this story in the rest of this lecture and maybe beginning of next lecture, there are other things that throughout the times becomes also more important. The second thing is the power consumption, because, for example, if you are using this battery power device, which is like an iPhone or cell phone, if you have a really, really fast device that only lasts for 1 hour, nobody's going to buy it, right? So you need to also be very efficient in terms of power consumption, right? So power consumption is another thing that these days are becoming important. The cost that somebody said is also very important. I can design this very, very great system, but if it costs twice as my competitor, nobody's going to buy it, right? So the cost is also important, but this becomes less and less important because generally the cost of designing hardware is significantly decreasing. And then also there is reliability and security, which is usually, unfortunately, what we call the second order problem. So people care less about reliability and security and care more about these other three metrics. But as it turns out, especially in the last few years of like we are being attacked left and right, now people are now care more about security, and that's what we're gonna mainly discuss in the other course next quarter if you're interested to take that. But security is also a growing interest in this domain. But as I said, performance is the number one, and as you will see in this course, all the decisions that we're going to make of changing this or adding that feature or removing that features is primarily motivated by performance. And the reason that we're doing that is just what happens in the past, and we're going to just tell the story of the past. So that's why we are focusing on performance as the number one problem in architecting, and number one objective of designing a computer. Okay, any questions? All right, so now let me talk about like the things that we did and the things that we're going to discuss in this course, and like the reasoning behind them. Okay, so if you're actually look at like the very first computer back into 1945 or something around that time, there was a big room even bigger than this, and the amount of computation that this big room could have done is significantly less than what Apple Watch can do these days. Okay, so that's how significant the difference if what we started with where we are is. Okay, and there are stories about this. If you're interested, go on and check it out. But the story is basically this important figures that we're gonna go back and talk a lot in this lecture. And we kind of like start with this like the first version of what is called like a personal computer, which is back in 1978 and around that time. And where we are at like this figure is a little bit older, so where we are at like 2018, which is like an Intel Core i7, which you typically use in your laptops. And the amount of speed up in terms of performance when we're going to talk about how we measure that, but for now just accept that this is a metric that we're going to use. The amount of speed up, the amount of changes that happens to the speed of the computers is around 50K. Okay, so the computer that we have these days, this laptop that I have in front of me, is 50,000 times faster than what we had in 1978. Okay, and not only that, but also the cost and the size significantly decreases. So we also getting faster computers, but we also getting much more cost-efficient computers, which is great. For example, if you look at the clock rate, which is this blue figure here, and the power consumption, you actually see that not only the power does not like grow a little bit, but eventually it's actually coming down. So our systems are getting more power efficient as well, and it's getting much more faster as well. So for example, the computer that we had in like the first version of Intel x86, which is 8082 and 86, the clock that it was using was around 12.5 megahertz, and your laptops that you're using these days are around 3.4 or even more gigahertz. So that's kind of like the range that we are seeing. So like 300 times faster, basically, in terms of just the clock rate. And on top of that, the interesting thing is that also these advancements are happening on the memory side as well. So it's not just processing. We're not just building faster CPUs, but we also building faster and much more bigger memories. So this is actually an interesting figure that shows that the biggest size of the memory in each year. So like around 1977, the first version was being introduced, which only has 16 kilobytes of memory storage. And then we had to spend about all the way to 2010 to reach to 2 gigabytes. And the interesting thing is that it only takes us 2 years to double that size. So we spend around 40 or more years to reach to that point, but it only took us 2 years to double, or less than 2 years to double that size. And that story is continuous. So we have terabytes of memory easily these days, which means that we are very, very also becoming very, very advanced in terms of building memories. Okay. So this is a nice table that, take a look at it at different numbers. I'm not going to go through them, but the one that I want to show you is that the price per computer not only actually increases because we are getting, obviously you would expect that now we are getting, significantly larger memory, significantly faster memory. At least there should have been this significant increase in the cost, but actually that doesn't happen. What we got is faster computers, bigger computers, and actually cheaper computers, which is really, really interesting. So now we know that the basic question is, okay, how did we do it, right? And that's the large part we're going to talk about in this course. But there are also things that we're not going to discuss in this course. And to give you a short answer of how we managed to have this significant improvements are two things. One is the advancement that we have in technologies. So we started with MOSFET, we make the MOSFET better and better and better. So it's kind of like things that we did at the device level, at the physics level. And then also things that we did at the entire abstraction level of computer science, and mainly at the computer architecture level, okay? So new technologies and innovative techniques, that's the main two reasons. So for example, if you look at the technology side, in 50s, we had like the first version of what we call transistors, that's basically vacuum tubes. And the relative performance per cost, if you normalize everything with that, what we have right now as this VLSI systems or ultra large scale VLSI systems, we are actually managed to, have a significant improvement in terms of the cost. So we managed to actually build these transistors and getting huge performance out of them with the same cost that we used for the vacuum tube. How we did that, that's a separate course and requires lots of knowledge about materials and devices, which obviously not going to go through, but probably some of you know like how we did and what we did with transistors. The important things about number of transistors, and something that you will see a lot and you probably have heard a lot, is this thing called Moore's law. So Gordon Moore was this prominent scientist, which one of the actual founders of Intel. And he had this kind of like quote unquote estimation or statement that the number of transistors going to be doubled every 2 years. And it turned out to be that actually what happened was like following very closely what he had predicted. So like this plot here, this points in this plot, the actual computers that's been rolled out each year. So you see, for example, the Apple 8-core Power 7 from IBM and all those things. And this is basically that line that says, every 2 years it has to double. And you can see that we kind of like, we very closely follow that trend. Sometimes we were a little bit better. Sometimes we were kind of like, behind. But overall, if you look at the trend in the last 30 or 40 years, you see that we managed to do that, like double the number of transistors every 18 months or every 2 years. And that's kind of like, the importance of this rule. One thing to note is that kind of like what this rule implies, or what this prediction implies, is that the economy of building transistors is getting better and better each day. So we basically managed to do cheaper transistors, and given that we do cheaper transistors, we managed to build more of them in the same chip with the same price. So assuming that we have budget of P, if we manage to build transistor with the half price as the previous generation, then we can basically pack twice as large number of transistors in the same chip with the same cost. And really what happens in reality was that these manufacturing companies get more and more efficient, that they manage to actually build smaller and smaller transistor with the same cost and with same equipments and so on and so forth. And that's how we got into this point that we have much more significant computer systems. And the sad story is that this is ending. So we no longer can actually double the number of transistors in a chip with the same cost, because the cost of building the next generation is actually not only reducing, but unfortunately is increasing, because the technology is becoming very, very complex, that you need to pour a lot of money in order to get to the point that you want it to be. So there's actually this notion that different depending on who are you asking. There are some people who say that the Moore's law has actually already ended. There are people that are saying that it's slowing down, and there are people that are like, optimistic and say that nothing has happened. But in reality, what has happened is that for sure the Moore's law is not the same as what we were expecting in the previous 30 years or so. We are seeing that the cost of building transistors is much more significant these days, and that means that the next generation of computers won't have the double number of transistors. What will happen is that actually we're going to discuss in the next few slides, but we still have the illusion that this is happening with other techniques that we are using. Another important impact about the Moore's law is that once we say that the number of transistors are doubling, the question becomes, okay, so what? So what is really happening in terms of importance of the important metrics that we talk about, importance of cost, the power efficiency, performance, and all those things. And generally, what this doubling, which we usually call it scaling, we are scaling from one generation to another generation, which is half the size of the previous generation. So we probably heard the numbers like 28 nanometers or 14 nanometers and all those things. So these are the generation of the transistors, which basically refers to the size of the pitch of the channel of one transistor. So basically this size. So for example, right now, Intel is saying that we are at like 7 or 10. Apple, I think the last iPhone that I saw, they said that they're at 4 nanometers. So what is really this does impact us in terms of at high level? In order to understand that, there's another prominent scientist called Dennard, which he has this scaling law, which is basically, it's not really a law. It's kind of like, analyzing what happens with transistors, and he give you this rule of thumbs that is very helpful. So basically what happens is that when we are saying that, the number of transistors double every 2 years, what happens is that in every dimension, we are basically seeing about 0.7x reduction, right? So if you're thinking about a transistor as this, L and X, in order to have the size that is like half the size of the previous, it means that the new L would be 0.7 of the previous L, and the X would be 0.7 of previous X, right? So so with that, let's see what happens to various things in our system. So for example, can somebody say what will happen to the speed of the transistor? Do you think that speed will increase or decrease? If it decreased, by how much, or if it increased, by how much? Generally, one transistor. When I'm saying about speed, I mean the switching speed. Like if you want to transition from 0 to 1, does scaling really impact the transistor or not? And if so, why? Anybody? Anyone who, yeah. Exactly. So yeah, exactly. So it gets faster. Why? Because think about it as like basic physics, right? The electrons needs to follow some distance from this side of the gate to this side of the gate, and their speeds are the same because they're kind of like speed of the light. But now we are saying that the distance is reduced by 0.7x. So So of course, this time it takes is also reduced by that factor, right? So we're getting much more faster transistor speed. So these are kind of like, you know, the summary of what Denners was predicting and what he was saying. I already talked about the speed, right? So what's called delays or speed is reduced by a factor of 30% because now it becomes 70% of the previous version. So we have faster transistors. The voltage to do the switching also reduces. Why? Because we need to keep the electric field constant on the channel, and since the size, the distance between the two you know, gates has been reduced, the voltage also has to reduce. Why we need to keep the electric constant? We don't care because we are at the computer architecture level, so we're not going to go deep into the transistor level. But just keep in mind that the voltage also has to reduce in order to keep the electric field constant. And as a result of these two, what will happen is that our switching frequency increases much more faster because 1/T is the frequency, and then we can switch this transistor much more faster. And remember, I told you about the clock frequency, and I show you that plot that is actually kind of rising from 12 point something to 3.4 gigahertz. That's exactly the reason that the delays is reducing, so we can actually switch the transistor much more faster. And another important thing is that the capacitance, which is also has a big impact on delays, also reduce. If you go back again to your basic physics, you will see that there is this formula for how we compute the capacitance. And if you plug in these numbers, so this K is a constant, but this A and L is the area and the length. And if you plug in these numbers, you will see that the capacitance is also reducing, which is also good news. We want less and less capacitance because capacitance means delays. So if you have less capacitance, we can charge the transistor faster. And that's also good news. Okay? Any questions from this slide? So this is the most transistor level thing that you're going to see in this class. So from now on, it's just going upwards. Maybe you get happier or sad, I don't know. Any questions? Cool. And then the last thing about this is what happens to the power? And anybody can answer this? What happens to the power? Well, obviously this is the dynamic power formula, so you have to just plug in the numbers. The power is reduced by how much? Twice, yes. So the power is half the power as what we have. How do we do that? If you go back to this slide and plug in all these numbers, you will reach to that half number, like 1/2. So the actual power consumption per transistors is reduced by a factor of 2, which is also great news because it means that, you know, if you're looking at the entire chip, what would happen to the entire chip? What will happen to the entire chip is that the entire power consumption for the entire chips remains constant. Why? Because we are doubling the number of transistors. And now each transistor requires half of what it requires to have, right? So still the number of transistors times the voltage is the same value, but now we have twice as large number of transistors, which is exactly what we wanted, right? So this is kind of like to recap of what happened is that with Moore's law and the way that we designed the transistors, we are doubling the size of transistors every 2 years. And the 2-year thing is because just the way that, you know, moving from one generation to another generation works. And there are lots of nice things happens as a result. The power consumption drops, the number of transistors grows, the transistors become faster, the capacitance reduces, and all those things. And that's how we managed to actually have this faster systems, this faster processors, and so on. That's how we start from this big room of ENIAC computer and now reach to this very, very tiny processor on your phone, on your wrist. And this is actually happens to be much more faster and much more cost efficient than the previous one. because we managed to do this with the technology that we use. Okay. Any questions? Okay, so this is kind of the advanced, short and brief introduction of what we had in terms of like technologies that we use. And this is basically, if you look at this plot that I'm showing, you'll notice that it's not the same slope. Slope kind of changing from one era to another era. And this first era, which between the 70s and early 80s, beginning of 90s, we actually managed to have speed of 25% speed per year. And this is just mainly coming from this device technology. We moved from vacuum tube to better transistors and better transistors, and we managed to make faster computers 25% per year. Okay. Then we reached to this second era that, as you can see, that is actually getting even faster. So 52% per year, we managed to make the computers faster. And this is what is referred to the golden age of computer architecture. There are lots of things that in the first half of the class we're going to talk about is actually happens during this era, which we do things like pipelining and branch prediction and all those things. And those are the ideas that happens in different industries and academia between the early 90s to early 2000. And this is basically, as I said, these are mainly advanced computer architecture techniques that we use to not only use the same advanced technology that we had, so we keep doubling the number of transistors and all those things. So those happens during this time as well, but we also managed to find these better techniques in order to process things and architect things faster. Okay. And the interesting thing is that this actually, at the end of this era, this was responsible for 25% faster computers. So if we hadn't done all those things, and only rely on the technology, we would have been 25 times slower than what we are today. And as I said, these are the things that we're going to discuss a lot in the first half of the class about what are those things and why they're important and so on and so forth. But also there is more. If you look back at that chart, that figure, you will see that there's also these other three eras. And what the bad news was that around 2003 or 5, that 52% becomes back to 23%, and then even gets lower and lower as we move forward, which kind of like now the era that we are. And that is what we call this specific time here is what is called the end of Dennard scaling, end of all these things that we said that, oh, the power stays the same, the transistor gets faster and faster. And the main reason for that is what's called a power wall. So around 2005, 2004, this very famous CPU coming out of the Intel, that they figure out that the amount of temperature and amount of heat it generates, if we actually start using the full performance, going to be even hotter than the nozzle of a space shuttle. That's how hot it can get. And it got to that point that you no longer it's safe to use a processor like this, okay? So you cannot really use the entire 100% performance of that processor just because of the temperature issues that it has, okay? So, and the reason for that is, again, if you go to a VLSI course, there will be lots of lectures about that. But we always thought that the main reason for energy and temperature was the switching. So if you switch the transistors, they dissipate some energy, and that's the reason for heat. At 2005 and after, since this size, this distance between this gate and this gate becomes so small that we also have leakages during the off period of the transistors, during the static part of the transistor when we are not even switching. And this becomes so dominant that regardless of whether you're switching this or not, it's gonna consume some power. And when you have billions of these transistors, then that's a huge number, and that's why this problem is kind of being created. This is like a very simplified version of what really happens. In reality, there are more things to it, but it's basically we are at kind of like, think about it as like, there are two energy levels, and there's usually a barrier, which is this gate. And when we are actually switching it on, we are reducing this barrier, and it goes down, and so that the electrons can move from left to right. When we are making this smaller, this barrier actually gets like very, very shorter. And what happens is that these electrons can actually jump. Why they can jump is quantum and all those things that we don't care. But what happens is that if this transistor gets shorter than something, then this electrons can start to jump, and it's significant numbers. So here they can also jump, but only like, the most athletic ones, they can jump, the younger ones. But here even the older ones can also jump. And that's the problem that we had with this type of transistor. So around 2005, end of Dennard scaling, all those things that I said no longer true. Okay? And this is what's called hitting the power wall, because the power was the wall against all these, new innovations. So we could not really reach to beyond that point, because there was this huge elephant in the room, which was the power, and we had to fix it. So what happened after 2005? The story continues, and as you will see in this course, that the story of designing processors and computers full of these walls, and there's also like someone or some groups that are coming up with some clever solution, and we jump over the walls over and over again. That's why people are not that much worried about Moore's law anymore, because they say that, oh, we have seen this too many times before as well, and we always figure out a way. And that's the story that happens during the 2005 as well. So what happens afterwards? That was the story of multi-core systems. So up to 2005, we had single core systems. There was like Pentium 3 and Pentium 4. There was just one giant processors. But Intel and the others come up with this very clever idea that, okay, we don't need to make one processor faster, but what we can do is that if we replicate two of those fast processors together, it's as if that we have one that is fast twice as fast, right? If they can work hand in hand very efficiently, it's as if that we are seeing it one, right? And as a user, we don't care. We think that we have twice. So if we manage to, have software and maybe divide it in half and say, oh, first piece run on this computer and this core, and the second piece run on this other core. And if they can work without any overhead, which in reality that's not true, then we have a twice as fast computer, right? And we don't need to make more transistors and all those things. We just can put more number of cores in the same chip, okay? And that's what we do after 2005, basically, okay? So this is just kind of like, this is just the things that I said in the previous slide. And then in the second half of the course, we're actually going to talk about multi-core, the challenges, and how we actually architected, and so on and so forth. Almost done. So then what happens after multi-core? So why didn't we have thousands of cores and then just be live our happy lives and call it a day? Unfortunately, what happens was just naturally the way we write programs, part of it are not parallelizable. So it's not like, oh, we can have 100 cores, divide the program into 100 pieces, and run them all in parallel fashion. Because there are, if you think about the way that we write programs, there is part that we need to read the inputs, we need to wait for something to happen and then do other things. And no matter how many cores you have to wait and pay that price, okay? So this is what's called an Amdahl's law, which is again another scientist and researcher, which basically come up with this law, which said that the amount of speed up, the amount of performance gain that you can get is limited by the amount of part of the program that you cannot parallelize, okay? So if we call this P is the part that you can improve, and S is basically the number of core that I have, the P divided by S is the part that I can improve, right? I can I can have 1,000 cores and make it 1,000 times faster. I can have 2 million cores and make it 20 million times faster, and so on and so forth. But unfortunately, the bad news is that there is this 1 minus p part that is what's called a serialized part, that regardless of how many cores you have, it only runs on one core. And again, examples are reading something from your memory, because you cannot, you have just one way of connecting to the memory. And regardless of how many cores are requesting that, only one can go through, right? So it's kind of like becomes the bottleneck. And if this P, for example, is like 80%, right? Then you're kind of like limited by that 20% at some point. So even if this becomes 0, then this becomes 0.2. And then at best, you can get 5 times faster. So if you have million cores, or if you have trillion cores, the best you can do is 5 times faster than what you have now, right? And that depends purely on the algorithm that you write. So it has nothing to do with the hardware or the speed of hardware or whatever else. It's just there are naturally algorithms that cannot be parallelized, and that's unfortunately the problem. Okay? So going back to here, at this point, transition to here is where we kind of hit that point in most of the applications. So first of all, these numbers are the average numbers. It's not like for single application. One single application can get faster, but on the average, we are kind of like slowing down because of that. Mm-hmm. Mm-hmm. So I'm assuming that this S is very, very large. So this term is like on limit is actually reaching to 0. Okay. So this term is 0. This is 1 minus 0.8, which is equal to 0.2 plus 0. So we have 1 over 0.2. And that's how I got to number 5. So I'm assuming that the P in this specific example that I'm giving is 80%. So 80% of my program can be parallelized, and 20% cannot be parallelized. Yeah. So it could be 90, 10, it could be 72, but 80 is kind of like a rough numbers that we usually have. Okay. Any other questions? Cool. So, and that's also ending, unfortunately, because there's also another problem added to all these problems that we have. And this is called dark silicon, which is kind of like similar to the problem that we had with Powerwall, but this time at the multi-core level. So remember I said that, oh, if I make this more transistors in one chip, it becomes so difficult to actually power it. Then we say, okay, how about we add more and more cores to it? At some points, you're going to also hit another limit, and that limit is that how much power can we actually pump through this chip, right? Because if you have 100 cores, all of them are going to like switch together, and all of them going to get hotter and hotter. But we have a very limited amount of chip silicon, amount of real estate that we have, and if you put more things to it, of course, it gets hotter and hotter. So at some point, there will be a point that we cannot really charge more and more power to the system, because it's just the whole entire chips that consists of multiple cores also gets really hot. And that's the phenomenon called dark silicon. And that's kind of like where we are right now, okay? We are hitting the Powerwall, we are hitting the dark silicon, we are hitting the Amdahl's law rule and all those things. And the question is what we can do next. Yeah, that's exactly one of the things that we're going to do. I'm going to stop here, and I'm going to quickly talk about what happens next, the things that we're going to do in future, actually. And then we're going to switch to the ISA afterwards.